So guys, as I've already mentioned, so now that this is the last part and the final part of the session, which is hierarchical clustering. So hierarchical clustering is already something I've already explained to you in the initial pages, so I'm not going to go down and explain hierarchical again. But the idea is very simple, right? That you have, earlier we were taking news articles and just clubbing them into sports, tech and say politics. But now we also want to kind of get a more granular level idea of what is there in sports. So sports can also be clustered into, there's a cluster of, within the sports cluster there would be also be subclusters of cricket, there could be subclusters of basketball, there could be subclusters of volleyball. Cricket can also have subclusters of T20, ODIs, and tests and whatnot. Probably it could have teams, so each of them could again have subclusters of teams and different levels, right? So the whole idea of doing hierarchical clustering is that there's a hierarchy of hierarchy of your clusters, right? So there's a big cluster which consists of all of your news articles. Then you kind of cluster them into something which is slightly less granular, something more granular, and then you kind of increase your granularity as you kind of cluster them further on and on, right? So that's the whole kind of hierarchical clustering. That means, and you keep on doing this until and unless you come up with points which are, each of the articles is basically a single cluster. Until and unless you don't reach that kind of a point, you don't stop, right? So that's the idea of hierarchical clustering. So I've already explained to you how this dendrogram looks like. So now, how do you implement hierarchical clustering? So clearly there are two ways to kind of do this, right? This is very simple. One is agglomerative or bottom-up clustering. What is bottom-up clustering? Is basically you start off at each individual data point and you kind of club them as you go forward, right? So the agglomerative, I'll clear this up. So agglomerative clustering is basically you start off at each individual point. This is a bottom up, right? So you're basically starting off, then you club this two, then you club this two, then you club this, and then you club this, and then you club this two. Say, and then you club this and this together, then you club this and this together, then you club this and this together, then you club this entire thing together. So that's the whole idea of bottom up clustering, right? So it's basically where you start off with a particular point, each points as single clusters, and then you kind of aggregate them as you go up. And obviously the other approach is top down, which is basically you start off with the entire data point as one cluster and you kind of separate them into different clusters. Now each of the cluster, then you again go back and separate them into different clusters. So that's divisive or top down approach. So as I've already explained to you, agglomerative is going up, bottom up, and divisive is top down. So which one to use? So agglomerative clustering is simpler to implement because agglomerative clustering is basically the one where you kind of sorry, it's not the case of agglomerative. Divisive clustering is something which is very easy to implement, which is the reason because divisive clustering is basically where you have the entire data point, then you separate them into different clusters. Each of the cluster you separate into subclusters. Each subcluster you kind of separate into its own individual subclusters. So at each step basically you can do something like k-means, right? So k-means is already a partitioning algorithm. You basically know what is that whole thing, right? You know that that's something that that is already there, that you can use and just do the steps of each of the steps, right? So this particular thing, right? The flat partitioning algorithm that you can use is called a subroutine. So you can use the flat partitioning algorithm to kind of do partitioning at each of the levels. So you can take all the news articles and partition them first into sports, tech and politics. Then you can take the sports one, again divide them into 3-4 parts, say cricket, football, volleyball. Take the cricket one, separate them into again 3-4 parts. So you can do that. That's something that you intuitively understand and is very easy to kind of implement also if you want to do it at your end. However, top-down routine has an advantage. Top-down is the one where you are kind of starting off and then you're kind of going down, right? You're kind of dividing at each step. So that has also another advantage. The advantage is basically this, that it is more efficient because you do not need to necessarily go down all the way to individual clusters. So if you're not going down all the way to individual clusters, you can save a lot of computational power there, right? So that's much more computationally efficient if you're just doing it, say, to third level. So you just think that probably sports has got multiple levels, and you just want to do it till that level. You don't want to see what's there in the inside cricket articles. You just care whether there's cricket or sports, right? So depending on the level you want to do, you really do not need to go down all the way down to the point where there are individual articles or single clusters, which is the opposite case in case of bottom up. In bottom up, you have to start off with everything that is at like individual level, they are single clusters, and then you kind of have to figure out a way to kind of combine them, and that is a problem because you have to do that all the way till you kind of reach a point where you have the entire data set. So in case of bottom up, you really don't have the flexibility to kind of choose where to kind of end the process. In case of top down, you have that flexibility. So given there is a fixed number of levels that you have fixed, so you want to go all the way down to just the second level, which is cricket, volleyball level, right? That's the level where it's a subcluster of sports. So given that there's a fixed level, so the number of computational power that would be required would be linear in terms of the number of clusters. So that's again one advantage of top down. And there's also some evidence that you can kind of check up on the links that says that divisive algorithms, which is basically the top down one, produces more accurate clusters. Well, this is something that I would want to take you with a pinch of salt, because this is not something that is entirely true, and this is just based on this particular study. It need not necessarily be universally true. It could definitely very well depend on the data that you have, but on an overall we can see that divisive top down approach is something that is easier to implement. It's much more computationally efficient and probably also produces more accuracy. So that's why, given the option, you might want to go with top down. So that's the thing. So now to understand this algorithm fully, there's only one bit which is left, which is basically earlier we were talking about distances between points, and we basically figured out that points which are very similar to each other, you kind of club them together, right? And we figured out how you do that. You basically had those 2 points which are your means. You calculate the distances of your points from the means, and that's how you figure out which cluster the points belong to. In case of hierarchical clustering, there's a slight bit of complexity. The slight bit comes from the fact that you have to now measure distances between clusters. If you remember this, in hierarchical clustering, you start off with points, right? So in case you are doing this, something like this, you have 3 points, and this has got say 1 point or 2 points out here, right? And then you have to measure distances between these 2 clusters, and say you have got another say 4 points out here, right? So you have to measure distances between, and then you have to decide whether you club this one to this or club this one to this, right? So to do that whole thing, right, to measure distances, earlier it was very simple. We knew distances distance between 2 points, which was simple, right? There was L1 distance, there was L2 distance, there was cosine distance. We had discussed all of this, but now we have to define distances between clusters, and because if these 2 clusters are something which are very short, we kind of club them together, right? So to decide which clusters to kind of club together, we have to kind of figure out the way to calculate distances between clusters. So that's something that is slightly bit different from the normal k-means distance calculation that you have seen. But again, this is not rocket science. This is something very easy, and the way you calculate distances between 2 clusters is basically very simple. There are only 3 ways. One is you take all the possible distances, right? So in this particular case, say you want to calculate distances between these 2 points, right? So there are 3 points here. Say we call them P1, P2, P3, and there are 2 points here, so we call them R1 and R2. So now you would have basically 6 distances, right? So you would have this 6 distances out here. So out of the 6 distances, there are only couple of things you can do. One is you basically, out of the 6 distances, you go for the distance which is the least distance, right? So basically the least distance would be the points which are closest to each other. So that is called, the minimum of this 6 is called single linkage. The maximum of the 6 distances is called double linkage. So when you are checking maximum, you are basically checking for the points which are the farthest away from each other, right? So you are checking the distances. Now this distances itself could be L1 distances, L2 distances are cosine distances, right? So any of these distances could be measured using anything. But what you are doing is basically now you are trying to measure distances between the clusters. So you have got the 6 point to point distances, and between these 6 points to point to point distances, you can take the minimum, you can take the maximum. If you take the minimum, it's called a single linkage. If you take a maximum, it's called a double linkage. And the other idea is you take an average of this 6, which is then called a complete linkage. So that's just the small bit that is there on top of everything you have understood. Rest of it is something you are already pretty familiar with. All we are doing here is basically calculating distances between different clusters, right? It's not anymore distances between points. Because we have to do distances between clusters, so what we do is basically take all the point to point distances that can be possible between the two clusters, and based on that, if we take the minimum, it's single linkage. If we take if we take the longest, then it's called complete linkage. My bad, this is nothing called double linkage. So this is called complete linkage, and this is called average linkage. So that's the whole idea, that you after 6 distances you take the minimum, that is called single. If you take the maximum, that is called complete, and after 6 if you take the average, that is called average linkage. So now SciPy has already, just to kind of note it here, you cannot, my understanding is probably you cannot do all of this in scikit. So we are using this library called SciPy, which is convenient library for implementing hierarchical distribution, hierarchical clustering. So the idea is very simple. You first define what is the linkage that you want to kind of use, and whether you want to go for average, whether you want to go for single, whether you want to go for complete. You just say that what is the linkage you want to kind of go, and then based on that linkage you can clearly see that this is the dendrogram that the algorithm has come up with, right? So this is the historic, this is the so this is, I'm not sure if you can see this, but this is a dendrogram that you can kind of come up with if you are using SciPy. So the dendrogram that I've already shown you, right? So that's similar kind of dendrogram you can see here, right? So it's, yeah, this is the one, right? Hierarchical clustering diagram. So you can basically see how the clustering has happened. So basically there's all the data, and that data is basically divided into 2 groups. This is the blue line, and then this is the one, and then this again has been further divided into 2 levels. So there's a lot of clearly this is the kind of dendrogram that we were expecting to see. And this, if you just check, just this is kind of for sake of your reference, this by default implies a top down mechanism for doing hierarchical clustering, the one that is used here, right? So that kind of uses top down approaches. So what are the different concerns between single linkage and complete linkage and average linkage? The concern is very simple, right? If you are using single linkage, you are basically looking at the minimum distance, which could be erroneous in case, say, the points are very far apart, right? There are there are only couple of points, so your distribution actually looks something like this, right? Say these are your different clusters, so there are a point here and there is a point here, and the distances between them is very low, whereas actually the original points are very far from each other. So because just these 2 points which happen to be very close to each other, it seems that because of single linkage you would come up with something, you would basically come up with something that is, these 2 clusters are probably very similar to each other, which in essence is probably wrong. The same problem in case of, say, complete linkage as well, right? In case of complete linkage, if you're trying to check if these 2 points are very far apart, right, and then the distances between them would be extremely skewed, whereas for the most of the points the distances lie somewhere here. And this is a similar kind of problem you can see in average linkage also, because in case you have extreme points, you are taking average, and average is something that can get skewed because of large distances, right? So even if you have very large distances, a couple of points, that can kind of skew your average, right? So that's a major understanding, that's a major problem between single, complete and double linkage. So how do you select actually what is the one to go ahead with? The very same way you had selected number of clusters in case of k-means, right? You just have to try out with different options and see which is the one that gives you the best results, because it's very hard to kind of predict what is happening at a cluster level, Even if you have the data about it, if you have the data, you would not be able to actually you would not be able to make an assumption about what is the correct kind of linkage that you should go for. So the best way to kind of do that is treat it as a hyperparameter and just try with different version of it. So that's the idea. So what are the shortcomings? One of hierarchical clustering, one of the biggest shortcoming is obviously that they're extremely calculation heavy, right? Just think about it. Every time you are calculating distances between two clusters, you're basically checking pairwise distances between all of them. That is extremely calculation heavy to start off with, right? And we're doing that multiple times over, right? It's extremely heavy, way more than k-means was. So hence they are not scalable. That means also they are not very useful for large data sets. So flat versus hierarchical clustering, obviously flat clustering produces a single partitioning. Hierarchical clustering kind of gives you a very nice granular level view, right? You can basically, it just doesn't tell you it's sports, tech or politics, it also says you what are the different things in sports. Within all those cricket also, what are the different kind of things that are there. That's something that's flat partitioning would not be able to tell you. The second thing is flat clustering needs a number of clusters to be specified. Hierarchical does not, right? It basically figures, because there's no number of clusters, right? It's basically just trying to go down all the way till it finds every point as single clusters. So depending on the level which you are looking at, right? If you're looking at the first level, you will basically have three clusters: sports, tech and politics. But if you go a level down, you would basically have cricket, volleyball, football, and then you would probably also have things under tech, and probably will have 15 clusters. So depending on the level you are looking at, you would have n number of clusters, right? So there's nothing that you need to specify in case of hierarchical clustering. In flat clustering, flat or partitioning clustering, you have to do that, and that's that's really, that's a drawback, because you really don't know always beforehand how many possible clusters could be there beforehand in the data, right? Until and unless you probably have been working on that data for long. And finally, obviously flat clustering is efficient, way more efficient time wise, right? I've told you that also earlier in the earlier lecture, that k-means obviously doesn't work very well for large data set, but hold on, compared to other clustering algorithms, it works way more computationally efficient than at least hierarchical clustering. So hierarchical clustering just goes for a toss if you have a large data set. So that's it. So obviously, given all of this, there's no final conclusion about in terms of accuracy or in terms of best clustering, which is the one. You have to obviously, like most of the things in data science, like the way you tried with different supervised learning methods, you have to also try with different clustering methods. So that's the end of the session. We basically learned of different applications of unsupervised learning, like PCA, dimensionality reduction techniques. We talked about kernel density estimation, we talked about clustering, but our major focus of the day was clustering. Clustering was basically this idea where you take data points, put them into different clusters such that items in one cluster are very similar to each other, items in two different clusters very different. Now, types of clustering, we had flat and partitional clustering where you have to specify number of clusters beforehand, and there was no subset, there was no relationship between the clusters that were formed. Opposed to that, there was hierarchical clustering where you did not have to mention number of clusters, and it basically gives you a nice hierarchy of all the different possible clusters. And then shortcomings of k-means. So k-means was the first first and the only partitioning algorithm we talked in the day, and k-means was basically consisting of two steps, where the first part was cluster assignment step, the second part was cluster calculating the mean step, right? So you kind of iterate between them and then you finally come to the solution. And we saw what were the shortcomings of k-means, that it does not work very well in case there's a non-linear cluster boundary. It doesn't work very well if there's a random initialization is not really good, then it kind of does not converge very well. In case of large data set, it probably does not work as much well. And so there were a lot of shortcomings that we had discussed. You can probably look back at the chapter and kind of look at all of them. And finally, hierarchical clustering was the last part that we discussed, which was basically very nice algorithm which kind of gives you granularity. It can be done in two ways, top down or bottom up. We saw top down was the most preferred one because of computational limits, but then again, in terms of accuracy, we do not know top down or bottom up which is the one to go ahead with. And there were different linkages that we saw that we had calculated for doing this hierarchical clustering. There was single, average and complete. based on the distance, the way you take min, max, or average. So that was about hierarchical clustering, and that's about it. That's a wrap from my end. See you guys next for the next lecture. Now let's head on to the assignment.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.